Hai, hari ini kita akan bincangkan chapter 3, Forces and Pressure, tingkatan 4. Okay, what is pressure? So, if we recall pressure, okay, P equals F over A, okay, whereby the force, it must be perpendicular to our area, okay, for us to calculate pressure. So what is pressure? So pressure is force per unit area. So that is pressure. So based on the definitions above, what is the formula for pressure and state its units? So we have mentioned it earlier that pressure equals force over area. Okay, force, the unit is in Newton, area meter square, so the unit for pressure is Newton per meter square. We have other name for this, and that is Pascal. Okay, PA, Pascal. Number 3, if you are to go chilling on the beach, which shoes below are you going to wear, and give your reason. So you have two choices, A and B, and you are going to the beach. Okay, so beach is sandy, right? So if I am to choose between A and B, definitely I would choose A. Okay, why? Because look at the sole for these shoes. Okay, the sole for these shoes, the area is high, correct? Okay, so if I go to my pressure, P equal to F over A, bigger area, okay, as my A increases, my pressure will decrease. Okay, so using these shoes, the pressure exerted on the sand will be decreased. Since the pressure is decreased, therefore the shoes will not sink into the sand. Alright, do you follow? Okay, so over here just now we have chosen shoes A. Okay, so we chose A. So the reason is the area is larger, hence the pressure would be reduced. I am just paraphrasing, sorry, is reduced. Okay, hence the shoes won't sink into the sand. Alright, question number 4. A table of mass 50 kg has 4 legs placed on the floor. Each leg has a cross-sectional area of 25 cm square. Find the pressure exerted on the floor. Alright, so I have a table. It has 4 legs, okay, and each leg, the area is 25 cm square. Alright, so the total area in contact, that would be 4 leg, right? So that will be 4 times 25. Okay, so I will have 100 centimeter square. Okay, so it's better for us to work in meter, so I am going to convert my centimeter square to meter. Alright, so I have here 100, okay, multiplied by centi is 10 to the power of negative 2, but here it is square, so again here I square it, and then at the back I only have meter square. Alright, so here you will end up with 0.01 meter square. Okay, and we are to find the pressure. So pressure equal to force over area. Okay, so the mass of the table is 50 kilogram. Okay, so mass is 50 kilogram. Therefore, the weight, okay, W equals mg. So m is 50, g is 10. So you will have 500 Newton. Okay, so force is 500 divided by the area 0.01. Okay, so you do your calculation, you should be able to get 50,000 Newton per meter square. Okay, now remember that this Newton per meter square, okay, other name for this is Pascal, right? So you can write the unit to be 50,000 Pascal. Okay, that's number 4. We go to 3.2, understanding pressure in liquid. What is the formula for density? So density equals mass over volume. Okay, so that is the formula for density. So look at question number 6. McLaren has a mass of 75 kilogram and then totally immersed in a tank of water, and then the water level raises by this much. Right, so this is the volume. Volume of what? Volume of McLaren's body. Right, so I have the mass to be 75 kilogram, and then the volume of McLaren body is 6.5 times 10 to the power of 4 centimeter cube. Alright, since the question asks us in kilogram per meter cube, so we are going to convert our volume into cubic meter. Okay, so here I have 6.5 times 10 to the power of 4, okay, times centi is 10 to the power of negative 2, correct? Okay, but I must take it to the power of 3. Okay, and at the back here I have meter cube. Okay, so if you do this conversion correctly, you should be able to get 0.065 cubic meter. Okay, so that is the volume of McLaren's body. So let's calculate the density. Alright, so density equal to mass over volume. The mass is 75 kilogram. Volume is 0.065. Alright, so you will end up with 1.154 times 10 to the power of 3 kilogram per cubic meter. Okay, so please verify that my answer is correct. Okay, my calculation is correct. It's 1.154 times 10 to the power of 3 kilogram per cubic meter. So that's how we calculate McLaren's density. Okay, the volume of the water displaced is equivalent to McLaren's body's volume. Alright, so we go to question 7. Formula for pressure in liquid. So the formula is pressure equals to rho g h. Okay, so this is the density of the liquid, and then h here is the depth. Okay, and don't forget that we measure depth from the surface to the point of interest. Suppose here is the surface of the water and here is the object. Alright, so the depth we measure from the surface here until this point here, okay, to the points of interest. So that is the depth. Alright, so the formula for pressure in liquid is rho GH. Okay, let's see question number 8. A balloon is located 10 meters below sea level. What is the total pressure experienced by the balloon given that the atmospheric pressure is 1.0 times 10 to the power 5 Pascal and then the density of seawater is 1100 kilogram per cubic meter. Okay, so I have here is the surface of the water. I have balloon here, okay, and the distance here is 10 meter, and at the same time I have P atmospheric. So what is pressing the balloon? Okay, whatever is above the balloon is pressing the balloon. So above, immediately above the balloon, I have 10 meter of water. And then above it, I have atmospheric pressure. Alright, so the total pressure at that point would be the pressure exerted by the water plus the pressure exerted by atmosphere. Alright, so P of water is rho GH, right? And then plus P atmospheric is 1.0 times 10 to the power of 5 Pascal. Alright, so we have the units are already in good term. We have kilogram, we have meter, here we have meter, so everything is fine. So just follow the flow. So the density of the water is 1100 multiplied by the gravitational acceleration, that will be 10, and then the depth is 10 meter. Alright, so plus 1.0 times 10 to the power of 5, and then we finish up the calculation. You should be able to get 2.1 times 10 to the power of 5 Pascal, okay, or Newton per cubic, Newton per meter square. Alright, so that is the total pressure, okay, exerted on the balloon 10 meter below sea level. Okay, so let's move to question 9. Water with density of 1 gram per centimeter cube and oil are filled into U-tube as shown in the diagram below, and we are to find what is the density of the oil. Okay, so I want to know what is the density of the oil. Okay, I'm going to use the notation O for oil, and then the density for water, here is water. Okay, the density for water is 1 gram per cubic centimeter. Okay, so how do I solve this problem? So first, we look at the boundary between oil and water. The lowest boundary is here. So draw a line, okay, draw a line here, alright? So from here, from this point to this point, the length is 12. From this point to this point, I have 10 centimeter. So what do I know about the pressure at this point, right? So suppose here I put here pressure at point A, here is pressure at point B. Okay, so the pressure at point A must equal to the pressure at point B. What is pressing point A? Okay, so I have pressure due to the oil plus the pressure due to the atmosphere. atmosphere, right? Because it's open here. So definitely I have P atmosphere pressing down on the liquids. Okay, so equal to the pressure at point B. What is pressing point B? Above it, immediately I have the water, and then above the water I have P atmosphere. Alright, so I have P of water plus P atmosphere. Okay, so I have P atmosphere in on both sides, so I can just cancel this because they have the same value. Alright, so P of oil, pressure due to oil, okay, exerted by oil is density of oil multiplied by G multiplied by the depth of oil. Okay, equal to pressure exerted by water, that would be rho of water multiplied by G multiplied by the depth of water. Okay, you see here I have G on both sides, so I can cancel out my G, correct? So density of oil, do we know? We don't know, right? So we leave it like that. All right, so here I have the density of oil, and then the depth of oil, or the height of the oil, is 12 centimeter, equals, okay, the density of water is 1, and then the height is 10 centimeter. If you notice here that I didn't do any conversion from gram to kilogram or centimeter to meter, alright? There's no need to do that because I can see that all my units are consistent. Here I have grams, centimeter, 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 centimeter. So they are consistent, so it's okay. Alright, so let's calculate the density of oil. That would be 1 multiplied by 10 divided by 12. So what do you get? Okay, 0.83 gram per cubic centimeter. So that is the density of oil. Simple, right? Okay, so first you need to identify the lowest boundary between the two liquids, the oil and the water. That will be here. And just draw the line, okay, and then you determine the length of this oil column and the length of this water column. Alright? And the pressure at this point and at this point, since they are on the same line, okay, so the pressure here and here, they must be the same. Okay, let's go to question 10. Diagram below, okay, shows a glass tube filled with 50 centimeter of liquid M and then 30 centimeter of liquid N. The density of the liquids M and N are given. Okay, the density for M here, okay, the density for M is 1000 kilogram per cubic meter, and then the density for N is 2500. Okay, 2500 kilogram per cubic meter. So if you notice here, I have kilogram, I have meter, and then here I have centimeter. So the units are not consistent. So I need to change the units so that they are consistent with one another. Okay, so my densities, I am using meter. So I'm going to convert my cm into meter. So 50 cm, that is equivalent to 0.5 meter. Just divide by 100. And then 30 cm is equivalent to 0.3 meter. Okay, now, so the question asks us to find the pressure of the liquid. Okay, so if that's the case, then we do away with the atmospheric pressure. All right. So the pressure of liquid M at point X. Okay. So we want to know what is the pressure at point X. Okay. So at point X, so we are here. So what is pressing this point? It's only the M liquid. Okay, liquid M is pressing at this point. Alright, so I will use my density for M multiplied by G multiplied by the height of that liquid M. Okay, so the density for M is 1000 multiplied by the gravity 10, and then the height, okay, the length of the column, the length of liquid M column is 0.5. Okay, so you do the calculation, you should be able to get 5000 Pascal. Okay, do you follow? Now let's go to question B. Okay, I want to know what is the pressure at point Y here. Okay, so what is pressing this point? Okay, I have 0.3 meter of liquid N, and then above that I have 0.5 meter of liquid M. Okay, so what is pressing point Y? I have pressure exerted by liquid N plus the pressure exerted by liquid M. Okay, so pressure exerted by liquid N, that would be rho N multiplied by G multiplied by the length of column of liquid N. Alright, and I don't need to recalculate my pressure exerted by liquid M because we have done that here. Okay, that is 5000 Pascal. Okay, so let's substitute all the value into the equation. Alright, so density of N is 2500, G is 10, and then H is 0.3, and then plus 5000. Okay, so the end result is 12,500 Pascal. Okay, check my calculation. Okay, so the pressure at point Y here is 12,500 Pascal. Or you can also write this as 12.5, okay, kilo Pascal. Okay, so let's move on to 3.3, understanding gas pressure and atmospheric pressure. Okay, what causes gas pressure in a container? There is gas pressure in a container due to the collision of gas molecules with the wall of the container. Okay, it's due to the collision. Okay, between the gas molecule, okay, gas molecules with the wall of the container. Okay, so you write the answer in good sentences. Just simply write down the keyword here. Okay, it's collision between the gas molecules and the wall of the container. This gives rise to gas pressure. Okay, 12. Name the instrument to measure gas pressure. So we've learned two gauges. The first one is the Borden gauge. And the second one is the manometer. Alright, so these are the instruments. Okay. 13. Name the instrument to measure atmospheric pressure. Okay, so here we want to measure atmospheric pressure. In question 12 is to measure the gas pressure. Alright. So what are the instruments that we use to measure the atmospheric pressure? So we have aneroid, aneroid, barometer. Another one is 14, barometer. Okay, so if for atmospheric pressure, it must have this word, this keyword, barometer. This barometer, it comes from this unit, bar. Okay, bar is a unit that we use to measure pressure. It's for pressure actually, whereby 1 bar, okay, 1 bar is about 1 atmosphere. Okay, it is about 1.0 times 10 to the power of 5 Pascal. It is not exactly equal, it's approximately. Right? So this barometer actually comes from this bar. That's why we have the word barometer, we have the word barometric. Alright? So it is to measure, is the measurements of atmospheric pressure. Okay, so let's go to question 14. Okay, now you are given a graph of altitude versus atmospheric pressure. So if I look at my graph here, okay, as my altitude increases, okay, I increase my altitude, what happened to my pressure? Okay, what happened to my atmospheric pressure? It is decreasing. Okay, if you go up a mountain, the atmospheric pressure will be very low. But we need to find out first, we need to know what gives rise to atmospheric pressure. How does atmospheric pressure exist? So if we remember our formula for pressure, P equals to F over A, okay? So at any place on earth, you have something above you, that is the air column, okay? You have air column above you that is pressing on you. So air, it must have mass. If it has mass, then it must have weight, right? Because weight equals mg. So what gives rise to atmospheric pressure? It is due to the downward force. Okay, the downward force exerted by the weight of air okay, on the Earth's surface. So this gives rise to atmospheric pressure. And then why is it if we go higher up a mountain, the atmospheric pressure decreases? Well, simple. It's because as we go up, the air becomes thinner. Okay. the air is thinner. So if the air is thinner, so the mass would be lower, correct? Okay, so if the mass is lower, therefore the weight of air should become lower as well. Alright, so therefore the weight of air is lower. So from our P equal to F over A, when F decreases, therefore P also decreases. So this in turn reduces the pressure or lower the pressure. Okay, so that explains why if we go up a mountain, the atmospheric pressure decreases. Okay, we go to question 15. 1 atmosphere is equivalent to how much? Okay, in centimeter mercury. So here is 76. Meter water, that will be about 10.3. But sometimes we use 10 lah. Okay. And then in a Newton per meter square, that would be 1.0 times 10 to the power of 5. Well, Newton meter square is Pascal. So here is the same 1.0 times 10 to the power of 5. Okay. If I add one more, how many bar? Okay, that is 1.0. Well, we try to be more exact. That will be 1.01325 bar. Okay, like this value to be exact is actually 1.01325 times 10 to the power of 5 Pascal or Newton per square meter. Okay, we go to question 16. Diagram shows a manometer connected to a gas tank. Determine the gas pressure given that the atmospheric pressure is 76 centimeter mercury. Okay, so I have gas and then I have mercury. So first determine the lowest available boundary between the two fluids. It's here, correct? So I will draw a line here. Okay, so if from this point to this point is 10, so how long is this point? So definitely here must be 14 centimeter. Okay, so I have centimeter, and here is also in centimeter. So no need for us to convert it to meter. Okay, now what do I know about these 2 points? So let's call here point A. Okay, let's call this as point B. Okay, the pressure at point A must equal to the pressure at point B. What is pressing point A? Is only the gas, the pressure exerted by the gas. Okay, so at point A, I have pressure exerted by the gas. Okay, now point B, what is pressing point B? I have 14 centimeter of mercury immediately above the point, and then above it I have P atmospheric. Correct? So I have here P, okay, P due to the mercury plus the atmospheric pressure. And what we want to find here, we want to find the gas pressure. All right, so P due to the mercury is 14 centimeter mercury. Okay, and then P atmospheric is 76 centimeter mercury. So we total these two figure up. You should be able to get that would be 90, yeah, 90 centimeter mercury. All right. So try to understand how we go about solving the problem. The same strategy, determine the lowest boundary between the two fluids, all right? And then this 2 point here, the pressure must be the same. Okay, let's move on. We want to do question 17. The atmospheric pressure is 76 centimeter mercury, and we want to know the pressure of the trapped air. Okay, what is the pressure here? Pressure of the air. Okay, this is what I want to know. Okay, so I will draw my line here. It's easier because I know from the bottom here I have P atmospheric pressing it up, but at the same time I have mercury, I have the air is pressing it down. Okay, so what do I know at this point? The P atmospheric must equal to the P due to the mercury plus due to the trapped air. Alright, otherwise the mercury and the trapped air, it will flow down. But in this case it doesn't flow down, so I do know that the P atmospheric here pushing it up must equal to the pressure exerted by the mercury and by the trapped air P. Okay, so we write the equation. Atmospheric pressure must equal to the pressure exerted by the mercury and the pressure exerted by air. Alright, so P atmosphere is given 76 centimeter mercury, and then mercury here I have 10 centimeter. So what is the pressure? The pressure of the trapped air. Okay, so now it's simpler, right? So the pressure exerted by the air is 66 centimeter mercury. Very simple and very easy. Okay, in fact physics is easy. So let's now go to question number 18. So I have a figure shows a simple 14 barometer used to measure atmospheric pressure. Remember, if you see this word barometer, it is used to measure the atmospheric pressure. Okay. The question asks you what is the pressure at point Q in Pascal. Okay, in Pascal. Alright, so you are given the atmospheric pressure is 76 centimeter mercury, and then the density of the mercury is 1.36 times 10 to the power 4 kilogram per cubic meter. Okay, so here I have vacuum, 10 centimeter of vacuum. What do I know about the pressure for vacuum region? Okay, the pressure must be 0. Why 0? Vacuum, there is no particles. If there is no particles, so there will be no collision with the wall of the container. Hence, the pressure must be 0. Okay, so we want to find what is the pressure at point Q. So what is above Q? I have mercury. Okay, I have mercury. And what is the length from here to here? The the length of the mercury column. Okay, so from here to here, do I know? Yes, I do know that my H here, it must be 76. This is my atmospheric pressure. It must be 76. Okay, so 76 plus 15, correct? So that will give you 91 centimeter. Okay, so that is 0.91 meter. Okay, do you follow? Alright, so the pressure at point Q, okay, so the pressure at point Q equals to the pressure exerted by the mercury plus above the mercury I have vacuum region, and I do know that the pressure here for vacuum region it must be 0. So I just put 0 there. So how do we find pressure due to the mercury? Okay, rho G H. What is our rho? Our density is 1.36 times 10 to the power of 4 kilogram per cubic meter, and then our G is 10, and then our H is 0.91. Okay, so plug the number into your calculator. You should be able to get 1.238 times 10 to the power of 5 Pascal. Alright,